Hello, everyone. Welcome back to your session of probability. Um, Last time we were talking about estimating or checking to see if the means of two populations are the same or different. And we said we can divide that into two different ways. Either the two populations are independent or dependent. And we said we are going to wait to discuss the dependence case till today. Last time we looked at if they are independent, now do they have the same variance or different variances? And we said that assuming different variances is always going to be our best shot. And we looked at both cases. Now, today we are going to look at when the two populations are dependent. And we said we usually design the experiment to be like that. It's better. Let me give you a couple of examples. Like, suppose we want to see how efficient is a new diet in reducing, the weight. So I can ask people who follow this diet, and those who don't follow it, and check the mean of, the mean weight of each sample. But that doesn't make any sense because maybe the people who are not taking the diet are exercising, or they are athletes, they are in better health. So what am I comparing? It doesn't make any sense. There are many other factors that are beyond my control, and I have no idea. Some are old, some are young, some are males, females, whatever. Another example. Suppose I want to see if two models of vehicles, which one has a better gas consumption? So the fuel consumption in one and the other. So I can I can let somebody drive one vehicle for like a week or through, specific period of time or mileage, and another to drive for the same other car several times or several cars from each model, and then compare the average. And then you say, wait a second, did you use different drivers? I say, yes. So who told you that one of them is a better driver in, like, he's driving slowly, the other one is crazy like me. So he's like, speeding up and braking and whatever, and that affects the consumption. So how do you compare them? So, oh yeah, you have a point. And then he said, did they go through the same route? I said, I have no idea. So maybe one was moving on a flat ground, or and the other one was like in a hilly road. So how do you compare? I said, oh yeah, you have a did they drive in the same weather condition? I said, well, I have no idea. You say maybe one was driving in like regular weather, the other one it was like rainy and or icy and whatever. So how can you compare? So, oh my God, I didn't think about that. He said, wait a second. I said, what else? He said, okay, did they drive in the same region? I say, no, which one? So couldn't one be driving on a highway and the other like in the city with traffic and stuff, maybe during rush hour, and the other one was driving? They say, oh my God, I never thought of that. So how do I do it? Okay. We said, okay, so let's see how many factors do you think affect that? And let's make them random. Meaning, I can let each driver drives half the time this vehicle and half the time that vehicle, but not in sequence. So I'm going to say to toss a coin again. So I want to tease you. I toss a coin. If it's a head, then I will tell this driver drive vehicle one. If it's a tail, I say drive vehicle two, and then maybe the same vehicle the following day will, and then I will let them go in the same under same conditions, same weather, same traffic conditions. They follow the same route, stuff like that. Okay, so now you say, oh, so now I'm taking off all the extraneous factors and concentrating only. If I see a difference, say, oh, that's most likely because this car is having a better fuel efficiency than the other. Now, if I go back to the persons who were taking a diet or not, I can get the same people who want to take the diet, for example, and maybe divide them into two groups. I let one group follow the same what they are currently doing, and the other I will give them a diet without, it's like, and then whether or measure the people who are taking, or if I ask everybody to follow the diet, let's put it this way, because I don't want to get you into more complications. So I'm going to weigh you before the diet and maybe 2 weeks after or a month later. And I see if there is and then of course we have to follow specific rules so that the comparison, if I see a drop in the weight, it's most likely due to the diet. So here we had two types of tires. I had a tire that was that we use in a vehicle, and then I was checking to see if a new tire on the market would be better. So they did something interesting in this experiment. They brought the cars, like 10 cars, and were checking the front wheels. So they had one type of tire, say on the right and the other on the left. And then if you say, okay, maybe turning in one direction, no, I'm going to make them random. So sometimes I put the new one in the right tire, or the right tire on the right or on the left, and do that. And basically, after driving like 40,000 kilometers, they measure the tread in each tire to see if there is difference. I wrote down the numbers here, and we see that, this is the new, as it looks like these numbers are mostly higher than the old ones. So we say probably the new tires are better, but I don't know how better. Is it really better significantly, meaning statistically better or not? These were 10 different vehicles, and each one was driven. It doesn't matter if it's the same condition, you see, because the two tires, I have one on the right, one on the left, and they are on the same under the same conditions. So if I see a difference, it's most likely due to the type of tire, not to some other factors beyond my control. That's how we do the um, the dependent. We design an experiment so that the numbers would be dependent. In fact, you can check these uh, and check to see the correlation factor between them. The correlation, we expect it to be high positive, right? I want it to be high positive. Why is that? Because remember, when I say now uh, x bar new minus x bar old, if I take the variance of that, remember we did that last time, is the variance of x bar new plus the variance of x bar old minus twice. uh, So when I say the variance, I mean x square, right? Minus twice x bar new, x bar old. So now if x bar new and x bar old are positively related, there is a positive correlation, then this value would be positive, and I'm subtracting twice that. So the variance of the difference would be lower, much lower. Notice the variance is a measure of error, right? So I'm reducing the error. I will have a very high power for this test than if I assume that these are independent. You can check, I don't know, I think I should have done that. Uh, so let me check something. I will go and change the lists, or maybe list let's delete those, clear them, since we already did this example before. Here I'm going to enter 435, 5, 421, 503, 571, 461, 4.7. Oops, it's only 4. Oops. What happened? Oh, I need to clear that. 4.7, 6.03, 3.8, and 4.7. So that's the first sample. The second sample, which is the old, is 419, 462, 404, found not found, 472, 552, 426, 427, 621, 346, and 4.5. So now if I go and do no, I don't think it doesn't do that, right? Let me see. There is no just no 2. I don't think that works. Oops. Delete that. What did I do? Okay. So sorry, I clicked the wrong thing. Calculate 2 variable stats. So L1, comma. I always do that. Nope. Second list, L2. Okay. I don't think you will get, yeah, it doesn't give you that. Oh, it gives you sigma xy. So sigma xy is 225. Remember, the expected value of x and y is the summation of xy minus summation of x times summation of y. So minus 4.814 times 4.579. And you can see that this number is large. 225 minus 4.814 times 4.579. And you get 202. So you are subtracting twice this value from the variance. You are reducing the variance very much. If they were independent and you use this method, it won't be good, right? Because the variance is still very high. Okay, so now we can find the difference. Let's call it D. This minus that is 0.16, 0.38, 0.17, 0.31, 0.19, 0.35, 0.43, and this is negative 0.18 because this one is lower than that for some reason, 0.34 and 0.2. Now, I will say the null hypothesis is D equals 0. The difference is 0, meaning there is no difference between the two. Versus the alternative hypothesis, now in fact I want the new to have higher thread than the old. I'm checking to see if it really has a better thread. So I would say D is greater than 0. That's the alternative. I will check at 0.05. But guess what? This is exactly like the 1T test now. I have 10 values and I want to check if the average is the mean 0 or greater than 0, right? So this would be mu d, of course, mu d. So I would say, okay, I will use the t statistic, and my t would be the average d bar, minus mu d over the standard deviation of mu d, which is s over root n. So t calc would be d bar minus 0, because that's the mu, I get it from here, over sd, the s of the difference, over square root of n, which in this case is 10. And then this value, I can construct a confidence interval and see that, or better even, I will do a test of hypotheses and find T alpha and degrees of freedom and 9 degrees of freedom. So this would be T05 and 9. What is this value? Compare those and calculate a p-value. Or better even, now I can go and edit L3, or does it tell you that you can, no, I don't think. What if I do, I don't know how to do that. I never did it. So it's better to go to stat, edit a new list, maybe list 3, okay? And enter these differences, 0.16, 0.38, 0.17, 0.31, 0.19, 0.35, 0.43, negative 0.18, 0.34, and 0.2. And now I'm going to go to stat, a test of 1t test. I have the data. Mu is 0. But now the list is L3. No, I want to change that. So I'm going to say the list is L3. Frequency is 1. I want to check whether mu is greater than 0, and let's calculate that. So I get t equals 4.25. The p-value is almost 0.001. So I will reject the null hypothesis that the difference is 0 and conclude that the new tires have better tread than the old model. So now I can use the new type of tires more confidently, right? And that's basically it. So now if I design my experiment carefully, trying to eliminate every other factors that I don't have control over and leave only the factor I'm studying, my experiment would be more appropriate and more powerful, right? To detect shifts, small shifts. So that's what happened here. Okay, and you can see that we got a very high T. Notice T05 and degrees of freedom, what that is. So inverse T, if I want to have 0.05 and 9 degrees of freedom, what happened? Oh, it's negative 1.8 or positive 1.8 if I make that 0.95 instead of 0.05, meaning if I come here, I should get the same result, but in positive 1.833. This one is 4.25, way down there. And that's what it tells me, that the new tires are much better than the old ones. I will stop here, and I think that was clear. Next time I will try to go over like I said before, the R Studio and try to solve maybe a couple of problems like that and show you how you can read it from files and so on. So on. Okay. Thank you for your time and see you soon. Bye.